Hey, it's Mr. Mulvicash again. I'm back with a little bit extra instruction on partial fractions, and I just wanted to do a couple more examples. The one first one here is an example where you don't have to have a constant numerator, right? You don't have to have a constant numerator, and at first glance, you might want to try to do something like u substitution, and like have some kind of form where you have this, right? Um, but if you let the denominator be u, this doesn't quite work out because the derivative of u is 2x plus 2, and we don't exactly have that. We only have a 1x plus 2 up there, right? So it's a little disappointing that maybe you could manipulate the numerator into this by adding and subtracting x, but then you're still going to be left with a complicated integral. So this integral should be done with partial fractions, and I'm just going to use the partial fractions technique from the previous video to do this numerator divided. I'm sorry, to rewrite this expression into a simpler form, right? So that's what I'm going to do. I'm going to take the x plus 2, and the denominator should factor, right? That's an important thing. We need to be able to factor to decompose this into partial fractions. So that should be x plus 3 and x minus 1. And of course, this is going to be equal to a over x plus 3 plus b over x minus 1. And you might have been wondering in the last video, like, what happens if I get these backwards? It's not a big deal. It's just that the a and b will switch, right? So my a might be your b, and my b might be your a if you put the factors in a different order. That's not a problem, right? It's not a problem. And the issue with this, right, is like you might be wondering, like, are a and b really going to be constants? And the answer to that is going to be revealed as I do this. So just kind of watch for a moment. But if you remember the trick, right, the equivalent equation that works for the numerators is going to be a times the b denominator plus b times the a denominator, right? And go look at the last video if you want to see why that's the case. But it's not hard to see that if x is negative 3, then that means that we put negative 3 into both sides, the x here, here, and here, right? That's what's going to happen. So we'll have then negative 1 on the left, and that's going to be a times negative 4 plus the b drops out, right? Okay. So that means that a should be 1/4. Okay. And if we use, let's see, x equals 1, and we put x equals 1 into all those places again, then we'll get 1 plus 3 on the left. I'm sorry, 1 plus 2 on the left, which is 3. And then we'll have the a drop out and b times 4. So that means b is 3/4. Okay. And it turns out that if you stick the a and b back up in the numerators, that it works, right? So if you have 1/4 over x plus 3 plus 3/4 over x minus 1, it actually works out. If you do 1/4 times x minus 1 plus 3/4 times x plus 3, that you get 1/4 x minus 1/4 plus 3/4, sorry, that's a 4, x plus 9/4. And look at here, this and this add up to x, and these two things add up to 8/4, which is 2, which is what we had in the beginning, right? So that's, yeah, it's kind of remarkable that it works out like this. All right, so then what we're going to do is we're going to take our original, integral and integrate the simpler form, right? We're going to do the 1/4 over the x plus 3 plus the 3/4 over the x minus 1. And let me erase all this stuff down here to give me some space. But I think you can see where this is going to go, right? I'm going to factor out those constants and use natural logs. And this time both constants are positive. So if you want to combine your logs in the end, you're going to use multiplication rather than division, like what happened in the previous video, right? So let's, oops, how did that all work out? That's crazy. Wow. Well, that's okay. I'll just erase some of it. I'm not quite sure what happened there. Just kind of undid everything. That's weird. Not sure what happened there. But in any event, we'll just scribble all this out on the bottom now. And so we'll have 1/4 factored out of our first fraction. And then the integral of 1 over x plus 3 is the natural log of absolute value of x plus 3. And then 3/4 natural log. So that's an acceptable answer, right? You could do like the natural log of, x plus 3 to the 1/4 times x minus 1 to the 3/4. That you could do something like that even, but this is totally acceptable, right? No need to go that far. If you try this, you probably won't mess it up, right? There's a chance of messing it up, so I wouldn't try that. Just know, though, that it could be written like that in multiple choice questions. Okay. Next example has, and we'll go do a third one in a moment, but next example, what are we going to have to do here? If you remember from the last video, since the denominator and numerator have the same degree, we're going to have to use long division, right? So we're going to have to divide x squared plus 4x minus 5 into x squared and add some missing terms, placeholders for missing terms, right? And so let me just complete this real quickly. And I'm not using synthetic division because the denominator is not linear, right? So we're going to subtract here, which means add the opposite. Right? So then let's see what happens. I have no idea what's going on there. I don't know why that disappeared, but anyway, they cancel out. So minus 4x plus 5, okay? So that means that our integral is going to be the integral of 1 plus negative 4x plus 5 over this denominator. And if you remember the previous example, on this second part, I'm going to use partial fractions, right? So this is a whammy of a problem, right? I had to do the long division so that I could have a smaller degree in the numerator, right? So the answer is going to be x plus the integral of this thing that I have to decompose using partial fractions. And I'm going to go ahead and put the factors in the bottom, right? So that should be what, x plus 5 and x minus 1, okay? So I have to decompose this fraction into some constant over x plus 5 plus some other constant over x minus 1. And that means that there's going to be an equation here where the numerator on the left, namely the one in the integral, is going to have to be a times x minus 1 plus b times x plus 5. And I'm going to use some convenient values here. So let's let x equals -5. And on the left, if I put -5 on the left side of my equation, that should turn out to be 25. And that's going to be a times -6. So that means a is -25 over 6. And let's see, if x is equal to 1, then the a drops out, and I'll get 1 on the left, right? -4 times 1 is -4 plus 5 is 1. And the a drops out, and I'll get b times 6. So that means b is 1/6. Great. So that means our integral here is going to be x plus the integral of what was a, -25 over 6 over x plus 5, plus what was b, it's our b now, is going to be 1/6 over x minus 1, and then we can do our integral all together now, right? So this is minus 25 over 6 natural log x plus 5, and then 1/6 natural log x minus 1, and they're of course equivalent forms because we're dealing with adding and subtracting logarithms. But if you can get this far, you get a lot of hand claps from me for sure. Okay, so just added example there where you might have to do some division first before carrying out the partial fractions. Okay, and this last example is not going to use partial fractions at all. And let me stop for a moment and ask you why. Why can I not use partial fractions on this problem? And hopefully you're looking at the denominator and you realize that it doesn't factor, right? You'd have to find factors where these numbers have to add up to be 3, but they have to multiply to be 2. And actually, I had that backwards. Sorry. I knew I said something wrong. They'd have to multiply to be 3, but add up to be 2, right? And so if I look at the factors of 3, like, that doesn't work, right? That's going to be positive 4, and that's going to be negative 4. And so I'm not able to factor this, right? So what do? Well, if you learn this in AB, you do something called completing the square. And I just want to illustrate kind of how that works, right? So what do I mean by a square? I mean that something like this. We'll just use a little a there. If I were to multiply x plus a out times itself, right, using the FOIL method, I'll eventually get this, right? And the greatest discovery I can make from this is that I know that a is 1, but if a is 1, right, I'm good, right? Then I could factor it into x plus 1, but it doesn't quite work that way, right? The a here is a 3, right? So what I'm going to do is I'm going to manipulate the denominator by taking half of this number and squaring it. So what is half of 2 squared? That's 1, right? And that magic number is the number that we want to see there. So what I'm going to do with that number is add and subtract it. Essentially, I've added 0, so I haven't changed the value of the integral. But what I have done is I've made it so that I have completed what I've called the square. So I'm going to do a little bit of moving things around here. Okay, and then this stuff is the square of x plus 1, right? That's what all this is, right? Okay, and then the other stuff is just a plus 2. Okay, so remember that the integral of 1 over u squared plus a squared du is 1 over a arctangent u over a. And so our u here is going to be x plus 1, right? And then, of course, du is dx, so we're safe there. But if a squared is 2, and what I mean by that is that that plus 2 has to be this a squared, right? Okay, so if that's the case, then that means a is the square root of 2. And, okay, so what our integral is it's... Okay, just trying to add on there. Hopefully I'll make this one work for you, but that integral was of this form. Right, and we said u is x plus 1, and a squared is 2, so that means a is square root 2. So what this should be is 1 over a arctangent u over a plus c. So I'll see if I can tack that onto the other video for you.